Afternoon, all of you. Today I am going to present my presentation AI-driven smishing detection in Android devices using TinyBERT and Aquila optimizer on the behalf of all the authors of the paper. This is my table of content. Firstly, I will give you the brief introduction about the topic, our contribution, proposed approach, detail about the simulation results, and finally the conclusion. So the portfolio of smartphones has significantly transformed the communication and information across, leading to increased vulnerability to various cybersecurity threats, particularly phishing attacks. Because as the because of the use of large amount of Android device or the mobile device, that the number of phishing attacks are keep on increasing. Because in this attack, attackers send a malicious SMS to a victim, which looks like a legitimate SMS come from some authentic website. And when user click a URL included in that SMS, he or she might redirected to a malicious website, and on that malicious website, all their credentials get lost. And so in this context, we need a sophisticated detection module that can efficiently detect the malicious SMS or malicious phishing attack tra traffic, and also not load the Android devices, because Android devices has a limited power backup and not and memory space, and not heavy algorithm work on the Android devices. So in this context, our contribution is to use we use a tiny but model for extraction of feature. We select the TinyBERT model because it is a transformer based model which is recently developed, and in the transformer based model can efficiently analyze the text and extract all the temporal and specific features from the text, and these features are helpful for the detection of the malicious phishing attacks. And we use a TinyBERT model because TinyBERT model is lightweight as compared to the full BERT model, and it might not load the Android devices. And along with TinyBERT model, we use an Aquila optimizer for selection of the hyperparameter. We select Aquila optimizer because it's more efficient as compared to other optimizers and lightweight also. So after using these two models, we achieve an accuracy of 96.881. We also compare our model with the standard deep learning model like GRU, LSTM, and SVM, and we see that our proposed model perform better than the rest of the models. So this is the basic of our theoretical approach. As we consider, this is the Android device, and when an Android device receives a specific SMS or some malicious SMS, this then this message is passed through a TinyBERT layer. This is the layer, and this layer extract the features from the text. These are selected features are extracted, and then these selected features are used by the CNN model to do the classification. As these features are extracted by the LSTM, so they are more exact or more accurate as compared to the traditional feature extraction model like what2 vector or another model like that. And here equivalent optimizer is used for the hyperparameter selection for the CNN model. We use dropout rate and learning rate for the CNN, and we get the optimum value of dropout rate is 0.25, learning rate to 0.001 for the by using the equivalent optimizer for the CNN. Now I will give the basic information about the data set and the simulation results. So we use SMS detection model, and we collect the data set from the cackle. Our data set consists of 5,574 English SMS messages, because so we mostly concentrated on the English SMS messages. In future we will try to increase the language to other data types also. But for this project we only focus on English language. So our messages are has two labels. Either it is spam or it is not spam. And this figure this represent the what clouds are specific top words which are like GOT, GET, URL, LG, call. These are the most frequently coming words in the data set. So first we check which are the most frequent word, and we remove the stopwords also because they doesn't repeat significance anything. So after removing the stopword, we pass through them to the part TinyBERT model for the data extraction of the features. So this is the representative TSN model for the extracted features. And in this in this the figure, each point represents the SMS message, hence displaying the cluster of data points. The colors signal the message label. Yellow donate the spam, and purple donate the not ham message, which means not a spam message. The division of the spam and ham clusters in the same region implies that the tiny but embeddings effectively capture the important variations between the two classes, therefore offering a strong basis for our smishing data detection system. This animation shows that how well the TinyBERT code elements that might distinguish smishing if attack from the SMS models. So this is basically the representation of the labels for the how the features are extracted from the TinyBERT model. And after extracting the feature, as I previously explained, we use hyperparameter optimization. So this first chart represents the diversity chart, which takes the variety of the solution over the iteration. Means how diverse is the model. We run the optimization for 30 epochs. Here we can see that, and and with the population size of 50. So of 50 population is select the best optimizer of the learning rate and the dropout rate. And here we can see that the is keep on varying. So that it has large amounts of diverse values from which it is selecting the most optimal values. And the second figure represents the exploration or exploitation part. Here we can say that exploration is more than 80%. It means that it is exploring large amount of new results. It it is not only concentrated on a single result or some specific result, but exploring more than 80% results. And exploitation here is less than 20%. It is not exploiting most of the resource system. So it is behaving like a lightweight model which use less resources and get large number of and as large number of values from that. And second is the global objective chart. Here we can see that the global objective chart get reduced and get fixed to a specific value. So this global objective chart help us to find the value of optimum value. It keep on changing as iteration increases, and as it reaches towards the final iteration, it gets the optimal value fixed. So it is the global optimal value. And here we can see the runtime charts keep on fluctuating because every model has some different values, and finally it will reach towards 5.75 seconds. So in 5.75 seconds, it get the optimal value. So it is relatively lightweight, on also its latency is also less. So after selecting the hyperparameters, we feed that hyperparameter to our CNN layers and finally get our results. So here we can say that, say, as I previously explained, our model has two levels, either as phishing or non-phishing or spam or ham, as we previously explained. And here we can say that our model can detect both of the level as 97% accuracy and 94% accuracy. Here it is 99% accuracy and 82%. So there is a chance for improvement, and in future we will try to improve these values from 82 and 88 to more than 90%. But currently also it gets an accuracy of 0.97%, which is effectively better than as percent to conventional models. And this is the confusion metric. It will give more exact matter. Like in legitimate, it get 882 times correct and 7 times wrong. And in spam, 199 times correct and 26 times wrong. So it is perform very well. But in future, we try to reduce these values so that our model will perform better as compared to other devices. And now we do the comparison also. This is the accuracy comparison. As I previously explained, we use GRU, LSTM, RNN logics. There is a simple neural network for the comparison. Here the blue color represents our proposed model, and these are represent this deep learning model. Here we can see that our model at the end of four epoch, or we run the CNN model for only for five epoch to make it relatively lightweight as compared to other model. So it will train very quickly and give the specific results. So our model reached approximately 97 or 96% at the end of five epochs. And this is the loss comparison. Here we can see that as the epochs increases, our model get loss value get decreased, which is less than 0.11115, and other models has loss value relatively constant and not get changed very much. And this gives the comparative analysis of accuracy. Previously chart presents for the only for the training accuracy, and this represents the accuracy for overall training and testing accuracy. Here we can see that our proposed method achieve an accuracy of 96.66661 as compared to only SVM is reach our model, but all other models are relatively less accuracy as compared to our model. And here we can see the precision. Here again we can see that our model achieved 96.776% accuracy as compared to other model. Only SVM is relatively closer to our model. And here again our proposed approach get accuracy of 96.881 on SVM get only 96.661. So our model has a relatively higher recall value as compared to the SVM and rest of the models. And in F1 score is also our model get accuracy 96.71 and SVM get 96.66661% accuracy, which is relatively less as compared to our proposed model. And finally, we conclude the presentation. So in this study, we propose a AI-driven smishing detection model for Android devices, leveraging the TinyBERT for feature detection and Aquila optimizer for hyperparameter tuning. The model was trained on publicly available SMS dataset from Kaggle, which we get processing and improving message clarity. We use TinyBERT for extraction of feature and CNN model for the classification. For this, we get 96.81% accuracy, 96.76% precision, 96.81 recall, 96.7% F1 score, and is performed relatively better than GRU, LSTM, and SVM based models. This is some of the references that we use to formulate our proposed model. Thank you.